going to finish off 7.1 today. In particular, we're going to look at two main questions. First kind of questions we're going to look at are ones where you use a U-sub first. And those questions, you're actually told to do it. So it's not like you need to say, well, how will I know? But hopefully you would know that in some questions, you can't do integration by parts right away. You have to kind of adapt the question to get it into form that would let that happen. So the first one where this happens is question 16. So it's, I believe, question 16, 17, and 18. These questions are very long because they involve so many different levels of work. And then the second thing that we're going to do is we're going to use what's called a reduction formula. And that's going to be question 19. So that's it, that's our goal. And it will take today to do that. You might think 4 questions, how long can that take? Yeah, it could take a fair amount of time. So we'll jump right into our first question. We are going to, what's that now? Number 16. We're going to find the integral of the square root of pi upon 2 to the square root of pi. And it's going to be 7 theta cubed, the cosine of theta squared d theta. Now this is a definite integrals. In other words, it's got limits of integration. For the sake of this question, let's just pretend they're not there for right now. We can worry about them later. So let's just focus on integrating this. You're told in the question to do a substitution. So we're going to do a U-sub. So here goes. Give me a U-sub. There's only one that's going to work here. What is that U-sub?
Theta squared.
Totally agree. Tell me why you picked it, because it's the right answer.
It's the thing inside the parentheses, and when you find the derivative, it will cancel out the other data.
Okay, sounds good. So cosine of ugly guy, use the ugly guy, right? And I'm just going through the standard process. Don't need to talk about it. You're comfortable about the U-sub, right? We've done 100 of those by now. Should be good at them. As I said, we're going to pretend those limits of integration aren't there. So it's going to be the integral of 7 theta cubed cosine of u times 1 over 2 theta d theta du. And I'm going to take that 7 and that 2 and call it what, 7 halves. Theta squared cosine of u du. Now, normally, if you get to this stage and there's some thetas left over, you're kind of worried, as you should be in many questions, but not this one. The thetas have to go away, right? Everything needs to be in terms of this variable u. So what can I replace the theta squared with?
With u.
With u. And just to make my life easier, can I suck out that fella there, the 7 halves? Now just keep him at the end. That way he's out the road, you know, he's there, but it just makes this guy a little bit cleaner. So we started off with this integral and it's now turned into this one. Now, when you look at this one, do you see a nice candidate for integration by parts? Great. Now, if we're going to do integration by parts, we need to find who f of u is and who g of u is. And it is important that we pick the right one. So which one is f of u in this question?
U.
Agreed. I think I called that situation 1, right? If it's a polynomial, u is a polynomial, isn't it? It's a very simple one, but it's still in the polynomial family. So its derivative is 1, and the integral of this guy is sine u. So everybody's happy with that. And so 7/2 u cosine of u du is going to be 7/2, and then we can put in our fella, our integration by parts fella. So it's going to be u sine u, take away 1 times sine u du. So it's going to be u sine u, and the integral of a sine is a negative cosine. 2 negatives make a plus, so we now have cosine of u. Are we happy up to this point? We're comfortable where everything came from? Right. What should I do next? I shouldn't leave it in terms of u, should I? Remember what the original situation was, what its variable was.
Do we just substitute theta squared back in?
Yeah. And then we can do it at theta equals the square root of pi upon 2, and theta equals the square root of pi. And I'm just going to dot that. Isn't that just plug and jog and you get an answer? And that is our first example of having to use a u sub to integrate something. And after the u sub, we then could do integration by parts. Oh, there's one of the 4 people that we should have. Now, that was 16 over with. Let's do a version of 17 now. And this is going to be the integral from 0 to pi. And let's just ignore the 0 to pi for the time being. We are being asked to do a u sub. And I like this question, even if you might not, because it does test something that we tend to get into a bad habit with. And the bad habit we tend to get into is thinking that the question that you're given is the guy that you are going to use. What do I mean by that? If I asked you to pick a u sub right now, none of the u subs you're going to tell me will work. I'll use, well, let's say you tell me, oh, let's make cosine t the u sub. That seems reasonable, right? E ugly guy, cosine t. Won't sine 2t not play well with the cosine t? Right? Doesn't cancel it. Won't cosine just turn into a negative sign? Problem. Okay, backup plan. How about sine 2t? Trust me, even uglier, still doesn't work. I'm getting desperate now. Well, maybe 2t, not even a chance in Hades. None of the u subs are going to work. And that means that we are going to have to find a different way to write the sine of 2t. Does anybody know a trig identity for the sine of 2t?
Would it be
Double angle, I heard. So 2 what?
2 sine t times cosine t?
Now, would you agree that this and that are the same thing, right? Now, tell me a U sub, because we do have a U sub that works now. What U sub would you use on this integral?
Cosine t?
Yes. And I'm going to go for e to the ugly guy, use the ugly guy rule, right? Now, if you differentiate cosine with respect to t, you get a negative sine t, because I have my differentiation. And I do a little move it along, right? Crossover, as I call it, and then divide by negative sine t. We have that. So we now have the integral of e to the u. I'm going to stick that 2 there because it looks nicer. We're going to have sine t u negative 1 over sine t du. Almost like magic. It works, doesn't it? It comes out quite nice. Right? All the cosines are replaced by u. The sine t's get cancelled out, and you're left with that. Now, at this point, do you recognize an integral that can be used integration by parts technique? So, who is going to be the f of t, and who is going to be the g of t? Who's f of t? Or I should say f of, where's the t coming from? I don't know where my brain is. There we go. Who is the f of u going to be in this question?
Just you.
I hear you. Do you want to expand it a little bit?
Do we want to make it 2u, or do we want to put the 2 outside of the?
Oh, we could do that. You could be, yeah. I mean, if you decided to do that, I'm totally with you. Is that what you were thinking? Okay, let's pretend it's that guy, in which case I like you. Agreed? And would you agree then that it's e to the u? And differentiate that guy, you get 1, and integrate that guy, you get e to the u. So we are now looking at negative 2, because we're doing this version. F of u, g of u, take away the integral of f dash g of u du. So it's going to be negative 2 u e to the u, take away 1 times e to the u du. And that is easy to do because you just get that guy. And I don't know, I'll probably bring out a u, an e to the u, I should say. Bring in e to the u. Got that. Right, it looks pretty. If there weren't any limits of integration here, this still wouldn't be correct. Shouldn't we have to return to the original variable? Are we happy with the answer now? Now, since it does have a limit of integration, don't we just take this guy and evaluate at t equals 0 and at t equals pi? And can I just dot that guy again, because it's just plug and chug. I mean, cosine pi's are going to be 1, and cosine pi will be negative 1, and cosine zeros will be 1. So that answer will probably turn into a relatively nice number, I suspect. to version of 18. We need a U sub. Who are you going to pick?
Natural log of x.
Correct. Why did you pick it?
We can get, it's gonna get us an x that we can cancel out with the denominator.
Sounds good to me. Actually, in this case, you don't need 4 lines, don't you? You get to the dx in 3. Sometimes that happens. So let's see what this fella becomes. He becomes the inverse sine of u, right? That's that guy, over x times x du. So it looks like we're now going to have to integrate that guy. That is integration by parts. I believe I called that situation 2. That when you have an integral and there's only one term, you can still use integration by parts. Who do you use as f of u and who do you use as g of u? Who is the f of u in this question?
Inverse sine u.
Okay, wasn't the rule when there's only one guy, he's your f of u? So who's g of u going to be?
1.
Right. And if you integrate 1 with respect to u, you get a u. Okay, cobweb time. Derivative of inverse sine of u. I think we did an inverse cosine yesterday, so it's not that different. Inverse sine of u.
1 over the square root of 1 minus x squared.
On this case, you're right. Yeah, u squared, but you were right. So we're good, right? So this fella here is going to be f of u, g of u, take away the integral of f dash g of u du. And so it's going to be inverse sine times a u, take away the derivative times u du. And I'll make this a little bit prettier. Oh no, would you look at what happened? I'll put them over here. We need to find out what this guy is. Normally this guy is dead easy, but not this time, because, you know, the last question, they're going to make it harder. What would you do? How'd you get this? How'd you integrate this?
We use u sub and take 1 minus u squared.
Right. Unfortunately, since our variable is called u, can I call it a v sub? Or any other letter in the alphabet you like. And if I differentiate this with respect to u, you get 2u. If you do the crossover, and then you isolate, So we now have u, the square root of v, times -1 over 2u dv. And that becomes -1/2 over that dv. And you know I like to separate the fractions. I mean, this one is fighting us every step of the way, right? Nothing's coming out nice, but we're still going to fight it to the end. I now need to integrate this. How am I going to figure out that? There's a clue. What fractional power will I turn 1 over the square root of v into? So I can use the power rule.
-1/2.
Right. Can you remember doing something like that in week 1? So, you know, just because it happened in week 1 doesn't mean that it, you know, whatever you learnt there isn't going to get used sometimes. Now, if you add 1 to the power, you get +1/2. Dividing by +1/2 basically cancels out with the half that's there, and you're looking at that guy. That guy is going to be called that guy. And that guy is now going to be called that guy. Are you happy about how this eventually became that? So I go over here. We almost forgot what we were up to. We have this fella. Take away that guy. Well, take away a negative means it's an add. So you've got this guy. And we should be really happy with ourselves. Hey, I think I finished. And you type it into WebAssign and it says you're wrong. And it's not because I forgot the +c. So let's pretend I put the +c in. It's still wrong. What have I still to do?
To go back to X.
Right. I'm not writing that down because I'm running short of room and I don't think it would fit. But wouldn't it be log x, inverse sine of log x, plus the square root of 1 minus log x in bracket squared plus c? So can I just go ... But that's what it would look like. Now think about that. What happened here is like the ultimate yucky question. You had a really ugly looking integral that you did a u sub, which turned it into something that looked relatively nice. We then used integration by parts, and it turned into this ugly guy. We had to fix this ugly guy by doing yet another u sub. And then we were finished. So what would that be? A u sub, an integration by parts, and another u sub at the end. So do you see how the mixing and match, you know, the mixing and matching of the techniques that we know can get us a lot more integrals now, right? We can now deal with more complicated situations as long as we keep track of what techniques are what. What do I mean by that? When I see that, I see a u sub. When I see this, I see an integration by parts. And when I see this guy, don't I see a fractional power rule? Now, in each one of those 3 situations, isn't part of the puzzle knowing what you're looking at and what method solves it, right? If you try to solve this with integration by parts, will you just trust me? You could do it yourself. It don't work. It never gets anywhere nice, right? If you try to do this with u sub, good luck. I haven't even a clue of what u sub I could try, right? I think that one's a little bit more obvious. Would you agree that one has to be a power rule of some kind? I mean, why would you try and u sub something that looked like that? So where am I going with this? One of the hardest things for students to recognize is what method should be used in what situation. And one of the reasons that happens is that don't you tend to get an entire section where everybody is just u subs, and then a whole bunch of questions where just everybody is integration by parts. So you don't need to worry about the method because it's the same method for every question. You see how it gets a little trickier once you start getting questions where it's not so clear what method. And that just, well, you'll get that from experience, you know. So far, so good. Right now, there is one more question that I'm going to show you. And this one is this guy. And I'm going to call this I. So I want to find the integral I. I want to find out what this is equal to. Is this going to be a U sub, even although I'm using the letters U? Is this going to be a U sub, or is this going to be an integration by parts? What's your gut feel? That's the only two choices I'm giving you because it's one of those two.
Would it be U sub?
I would start with sub.
And Caitlin, what were you saying? I kind of broke up at the end, so I didn't catch it.
I said U sub.
Okay, so what U sub are you thinking?
I would do the 2U because it's the ugly part of the E.
Totally sensible thing. Can you trust me that 5 minutes later you find out nothing works? Okay. Is there any other candidate for a U sub in this question? Maybe cosine U? Can you trust me after another 5 minutes it doesn't work? So no U subs that you could try would work in this question. Now, how do you learn that? You learn it by doing exactly what you did. Quite reasonable. 2U is a very good U sub in many questions. I wouldn't argue with it is. But you try it out and it just doesn't go anywhere. And so you try some a little bit unusual, maybe a cosine U, and it doesn't work. And what you've learned then is don't use U subs with questions that look like this. Which means then, by a process of elimination, it has to be, because nothing else works, it has to be integration by parts. And let me warn you right now, it's going to look like it doesn't work. But you have to persevere, and I'm going to show you a little sneaky trick at the end. Okay, who are you going to make F of U and who are you going to make G of U in this I've never seen one like this before situation? What do you do? Who's F of U?
Cosine?
You want to do cosine? Okay. So won't the other guy be the G? And if you differentiate a cosine, you get a negative sign. And if you integrate that guy, you get 1/2 e to the tu. So you should be hesitant because how do you do a question you've never seen before, right? You don't know. You don't have anything to base it on. Can I tell you the good news? You could have done it the other way around and it still would have worked. So that's the good news, right? So this is a situation where either one would have done. Now we're going to put this package together. And as I warned you a few moments ago, it's going to look like it doesn't work. But it does eventually. So it's F of U, capital G of U, take away the integral of F dash G, capital G of U, du. And this guy is cosine U, and this guy is 1/2 e to the 2u. Okay, that's good. Take away the derivative, which is negative sine u, and that guy is 1/2 e to the 2u du. So I'll just make it tidy. It's 1/2 e to the 2u cosine u. Those two negatives cancel out. You get a plus, and you get 1/2 e to the 2u sine u du. Would you agree that the leftover integral is slightly uglier, but looks quite similar to the start integral? The way integration by parts works typically, doesn't this guy become a little bit easier to do? He becomes a little bit simpler. And then you may have to do it again and it becomes simpler, but doesn't look that promising right now. But nonetheless, trust me, it is going to work. Put a little bubble around that. Okay, I need to figure out this guy. So I'll just move it over here a little bit. For this integral here, who am I going to call f of u and who am I going to call g of u? Okay, who am I going to call this guy? F or g? Be consistent.
G then.
Okay, so I'm going to pick this guy and make him g and this guy's f. What do I mean by be consistent? If you ever get an e to the something and a sine or a cosine to something, you know, this kind of shape, if you decide to make this guy a trig, always make the f a trig. If you decide to make him an e to the u, always make him an e to u, right? That's part of what you have to do. So it's going to be f of u, g of u, take away the integral of f dash g of u du. So it's going to be 1/2 e to the 2u cosine of u. The f is sine u. And if you integrate this guy, you get 1/4 e to the 2u. Take away, if you differentiate a sine, you get a cosine. And integrate this guy, you get 1/4 e to the 2u du. So what I'm now going to do is make it look a little bit prettier. This guy can be written as 1/4 e to the 2u sine u. Take away, I'm going to bring this 1/4 out. And what I'm going to be left with is e to the 2u cosine u du. So we have now done integration by parts twice, and we're left with two terms minus an ugly integral. Now, would you agree if I kept on going, I would continue to get different ugly integrals, right? But I'm not going to. Because do you notice this ugly integral is actually the guy you started with? And isn't all of this, right, this entire mess, trying to find the guy you started with? That means that the original integral is 1/2 e to the 2u cosine u plus 1/4 e to the 2u sine u minus 1/4 the integral at the start. Now, this is not like any typical integration by parts. We did it twice, and we found that the integral you started with was this ugly mess. Take away 1/4 the integral you started with. Any ideas what's going to happen next? Because we're 2 lines off the answer. Remember, the goal here is to find out what the integral is equal to in terms of just u.
Add 1/4 I to both sides.
And if you add 1/4, you get 5/4 I is equal to this. Okay, this is it. How do I find I, the integral I was trying to get right at the start of this question? I know what 5/4 I is equal to, but how do I find I?
Multiply both sides by 4/5.
Okay, divides both sides by 5/4, which means multiplied by 4/5. And if you do a 4/5 of this guy, you get 4/20. 4/20, God, that's a hard one. You don't, 4/10, that's better. 2/5. Plus 5 of these. So what we have found is how to do the integral of a combination of e to the power of somebody, cosine of somebody. This same technique will work for e to the power of something, sine of you. It uses integration by parts, agreed, but doesn't it use it in a way that none of the others ever did? So just because we have a rule doesn't mean that sometimes you have to maybe do a u sub before you can use it, or that sometimes you might have to turn one of the pieces into something else before you can use it, or that maybe you can do an integration by parts and then later on you have to do a u sub, right? There are lots of different flavors to this process being used. It's not a, one size fits all. Really like that question, just because of how weird it is. Yet it successfully got the answer we were wanting. So we're now on to our last question. We're going to use what's called the reduction formula. And it's question 19, and here is the reduction formula that you're going to use. A reduction formula is a formula that allows you to find the integral of families of functions that share something in common. This particular one is going to be a formula that allows us to find the integral of sine cubed x, sine to the 5x, sine squared x, even sine to the millionth power of x if you felt like it. And its formula is given to us. So it's -1/n, the cosine of x, sine to the n-1 power of x, plus n-1/n, the integral of sine to the n-2 power of x dx. And it's called the reduction formula. And there are reduction formulas for the cosine to the nth power and the log to the nth power. They're the three most common. So let's use it to find sine cubed. So let's show you how you do a reduction formula. This fella n is whatever the original power is. So that means n is going to be 3. So I just go through this entire formula, and anytime I see an n, I replace it by 3. So -1/n becomes -1/3 cosine x times the sine to the n-1 power. Well, if you have 3 and you take away 1, you're going to get 2. So that becomes sine squared x. Plus 3 take away 1 is 2/3. So that's 2/3. And this fella, the sine of 3 take away 2, well, that's 1. So you just get the sine of x dx. Are you happy about how this formula for sine cubed became this? Now, do you notice that you've still a little baby integral at the end that you need to finish off with? So let's finish off with it then. So it's going to be -1/3 cosine x sine squared x. If you integrate a sine, you get a negative cosine. And you're done. if you look at where does this horrible thing come from, right? Can you trust me that it actually comes by using integration by parts? And they got this formula by taking the sine to the nth power and splitting it as a sine x times a sine to the n minus 1x. And if you do that, this is the formula that you got. Let's try it for a higher power. Last question, this one. Now, in this case, n is going to be 4. So negative 1 over n becomes negative 1/4. Cosine x, n minus 1, 4 minus 1 becomes 3. So that's going to be sine cubed of x plus 3/4. And sine squared x dx. Okay. How do you think we're going to get the answer to sine squared x, this piece? How do you think I'm going to get the integral of sine squared x?
Repeat the process.
Correct. What will be the n value that we will use in this repeat the process? What's the n going to be this second time round?
2.
2. So negative 1 over n becomes negative 1/2 cosine x. 2 take away 1 leaves you with 1, so that's sine x plus 1/2 the integral. What's the sine of x to the power of 0? Interesting.
It's just 1.
It's just 1. X to the 0, e to the 0, sine x to the 0. If you take any expression but raise it to power of 0, you get 1. So what do we get then? We get negative 1/4 cosine x sine cubed x. Might as well distribute the 3/4 while we're at it. 3/4 times this guy is negative, well, too many negatives there. Negative 3/8 cosine x sine x plus 3/8x, because you integrate 1, you get an x with a c. And we have now done the reduction formula. Can you see that this formula, theoretically, couldn't I do sine to the 100th power of x? But you know, you better pay me a lot of money if you want me to do that. Wouldn't that take you for a long, long time? So it's really useful, yeah, but don't you want to keep the powers less than 10 at least? Probably only up at sine 4, sine 5 before it becomes cumbersome. But, you know, it does the job. And it's called the reduction formula.